All right, it's peanut butter and cryptography time. And we're out of peanut butter. Okay, so let me adjust the camera 1 second. Make sure my hair don't get in the way. All right, good. Good, should have done this before, but it's okay. Guys, I'm excited. New markers. I finally have a nice black marker for you so you can see better, okay? All right, let's get started. So today we're talking about quantifying security. Last time we talked about defining what's impossible, etc., etc. Today we're quantifying security. So we're defining wow. All right, perfect. We're quantifying security. So we're gonna look at, let me put silence. All right. So we're basically answering the question, how efficient and how practical is an attack? So we have an attack, and I want to see how efficient and how practical. Okay, we're gonna try to answer these questions about an attack on cryptography. Cool. So how do we measure security of again, in a theoretical way? We measure it in bits, okay? So I don't know if you remember, we did define a notion of security before, which was T-secure. Okay, T-secure. Where T is the number of operation, right? And obviously, I mean, actually it was T and epsilon security, but epsilon will keep it at 1 because we will consider obviously the best chances of so we always define security before as T secure, with T the number of operations. How else can we also define it, right? We can say that a cipher is an bit secure, okay? What does that mean? That it's gonna take to the n operations, oh boy, to break or for the attack to succeed, okay? It means that you need to do 2 to the n operation for your attack to succeed, right? So what does it mean? How do we get to the number? We take the binary log of the number of operations, so of T, okay? So if we have, example, a cipher a key that I can break, I can guess in, let's give it a T of 1, 2, 3, 4, 1, 2, 3, 100,000, right? Let's see that I have a T. The way we get to the n-bit security is that we take the log base 2 of this number, okay? And that's when I get more or less 20, because 2 to the 20 is equal to more or less million. And that's when we have that this is 20-bit secure, right? Yeah, it has 20 bits of security. Perfect. So again, if we have therefore a key of n bits, so 128-bit key, then we have a 128 bit security, because it means again that we need to do 2 to the 128 in this example operations to break and to find the key, okay? But that's just an upper bound, okay? It can be lower the 2 of the n operation in 2 instances. One is when you're a clever attacker and you find a subset of a smaller pool of operations to try, and therefore you do it in a less number of operations than 2 to the n, or if intentionally the algorithm is being made so that even if I think RSA has 40 bit key, but it's obviously reduced to a 128 bit complexity, I think. Yeah, the cipher security level, yeah, as with the most public key algorithm. For example, the RSA algorithm with a 2048 bit secret key provides less than 100 bit security. So keep this in mind. Right, this is great, okay? So we know that if it takes a certain amount of T operations, for example 1 million, to break a cipher, then we can calculate using this formula. Let's see. Yeah, can I generalize the formula here? Log 2. We get to this by doing oh shit, LG. Again, I'm too focused on the G. There you go. Log 2 of T, okay? Exactly, of the total amount of operation, and that gives us the operations to break. Cool. So great, we know the bit security now, we know this notion. But it's not telling us in real life practical what is the cost, what is the real cost of my attack. Okay, it's 40 bit secure, it's 100 bit secure, I get it, but what is the real cost of the attack, right? Okay, 1,000 again, 1,000 operations, 1,000,000 operations, 100,000 operations, 100 operations, but what is the cost of this operation? This is not telling me too much in real life, right? So, let's take 2 ciphers. Cipher number 1 and cipher 2, okay? These have the same, let's say, 100 bit security. But let's consider that. So theoretically they have the same bit security, right? They should be the same. But they can be different, because if this cipher is slower, meaning it takes a bit more to run this cipher than this one, right? Slower, faster. Then if you brute force this versus if you brute force that, if both need 2 to the 100, right, which means 2 to the 100 tries to find a key, we're gonna be much faster in doing these tries here rather than doing them here. So we can say that these 2 ciphers, yes, they have the same bit security, but cipher 2 is way more secure, because an attacker has to put a lot more energy and effort into testing into the brute forcing, for example, this algorithm, right? And this one, can we say it's a little bit weaker, even if they have the same n-bit security. So n-bit security is a theoretical way to give to quantify security in a cipher. In real world, the same bit security may result in different costs, and we're gonna look into this. We're gonna keep talking about this. So let's find the cost of operation. And actually, before even going there, I want to, let me see, where can I write this? And cost, and then choose a good number. So let's find, okay, cost of operation. Because again, we talk about operations, but how do we find the cost, the real cost of the operation? versus. So the cost of operation depends in four main things. One is the parallelism. Okay, parallelism. And parallelism just means running computations in parallel. So if I have a let me see here, if I have 2 to the 56, if I have 2 to the 56 operations, right, if I need to do 2 to the 56 operations, to break a cipher, there's a big difference if I have to do them all in series, so that you run one computation and then you run the other one and then you run the other one and then you run the one, and then you have to wait for this computation to finish to go from the next one, then you wait and you go for the next one, right? This is in series. But in parallel, they're all executed at once, okay, if this makes sense. Versus one after the other. Okay, you have to wait for the previous one to finish, then you start the other one, then you start the other one, 2 to the 56 times. While here, maybe you have, I don't know, 2 to the 5 processors, and so you can run so many operations at a time. Before then you can run these operations, and so you're doing everything in parallel. You're batching, you're doing in batch a lot of operations at the same time, so it's more efficient, it's better, less cost for your attack if you can do it in parallel. Okay, in parallel, use the parallelism. And the more processors you can add to a parallel operation, so the more you can batch together, and the faster it scales linearly. Okay, you linearly become more powerful, more stronger in doing that attack. Perfect. The next one, let's see if I can write attack in parallel. Okay, then the next one, characteristic of cost, is going to be memory. Right, memory costs money. It's computer real estate, right? So with memory, we want to know how much space, so the size of the attack, of the data that we need to move from memory, the memory lookups, how many lookups our attack needs to do when breaking a cipher, accesses, speed accesses, and access patterns. Okay. What I mean to access patterns is that where are you accessing your data? Because to access data in your register, it takes one CPU cycle. To access data in your memory cache, in your cache memory, it takes 20 cycles of processor. While accessing data in your DRAM takes 100 cycles on your processor. So again, big difference. An order of 100 processor spins is a big difference. Can make a huge difference. So memory. Always consider how much memory, how much the data that we're moving in our attack, how much memory it consumes. That adds to the cost. And again, an attack that uses memory, that uses less lookups, a series of operations that use less size, less lookups, and less access patterns result in a cheaper attack against a cipher, okay? Parallelism, we did it. Precomputation. Okay? Precomputation is basically the offline phase of the attack, if we can call it. If we can call it like that. So it's something that you do only once before your attack. And so it's something, for example, lookup tables. Right? So you run these operations before attacking the cipher. You build a series of tables, right? And then use those tables during the attack to reference, etc., etc. And a good example of this, you should Google and find more out about it, is the 2G, when they broke 2G encryption. So to break 2G encryption, they had to run pre-computations for 2 months in advance, and they gathered around 2 terabytes of lookup tables before being able to attack 2G communications. So that's pretty cool, and that's something to consider in the cost of operation. How much pre-computation, how much work you have to do before attacking. And then, last but not least, the number of targets, right? You might think, oh, the more targets you have, the more expensive. But think again. So you have targets. Let's write it this way. We have a lot of targets, right? Which means you have a big attack surface, which means we have, again, assuming that all we care is finding one key in many targets, then we have more chances. To find the solution. To attack, to succeed. There you go, succeed. Well. Okay? Now, why? If we have, let's say, a 128-bit key, make an example. Okay, 128-bit key. Okay, we have to find keys, at least one key, out of let's see how many targets you get. 2 to the 16. So we have 2 to the 16 targets, right? That means that compared to finding only one key, which takes 2 to the 128 trials and etc. Now, if we only need to find one among these targets, then we only need to do, which is 2 to the 1, 1, 2. Okay, so we just reduced the time from 2 to the 128 operations to find one key of one target to 2 to the 112 operations to find at least one key out of all of our targets, which are a lot. There are 2 to 16. Okay, so just to give you an example of how the number of targets can affect the cost of operations. Okay, now that we know this, let's go to the final part of the video and talk about how choose and evaluating security levels. Okay, so most modern crypto has, make a divide here. Okay, good. So choose and evaluate the security level. Most crypto has comes in 128 security or 256 bit security. Okay, so this means So security. Just to give you, actually, let's focus on the 128-bit security for now. Let's talk about this because it's interesting. Let's take the 128-bit security and let's give you. I'm gonna give you a little bit of a perspective. I was shocked when I learned this. So again, we have a 128-bit key, right? So 128-bit security in a cipher. That means that we need to have 2 to the 128 operations, right? To break a 128-bit security key, right? Guess how old is the universe? The universe is 2 to the 88 operation. Is 2 to the 88 is 2 to the 8 nanoseconds old, right? Consider that one operation with a modern computer, with a modern processor, will take 1 nanosecond. Okay, that means that you have that you need to basically, it will take you 2 to the 40 to break the encryption key. Okay. Just make sure I'm not throwing crazy numbers. Yep. Yeah, you need several times 2 to the 40 times of the age of the universe to break this encryption key. How crazy is this, right? So 128-bit security, pretty secure, right? But so, okay, so we need to spend 2 to the 40 times the age of the universe, okay, to break a 128-bit security, a key, a security cipher. So what if we have parallelism and many targets? Because again, we said that parallelism and the number of targets, they affect the cost of the operation. They make it better, quicker. They can make it quicker. So let's do this experiment. So what if, okay, what if I have 1,000,000 cores, right? And I can cut the search. Okay, I have 1,000,000 cores and 1,000,000 targets, okay? 1,000,000 cores and 1,000,000 targets. What's gonna happen? Then I'm just gonna have, so with 1,000,000 cores and 1,000,000 targets, then I'm just going to have 2 to the 128, okay? Divided by 2 to the 20, so 1,000,000 processor cores, which makes it, 2 to the 20, reduces the parallelism, right? Makes us be quicker because we can try many keys at once instead of having to do one by one. So it reduced by 2 to the 20, and we have 1,000,000 targets. So again, divided by 2 to the 20, 1,000,000, okay? And so this gives us Unfortunately for the attacker, fortunately for who's implementing the 128-bit security, it's given still 2 to the 88 operations needed to break this 128-bit encryption, right? Which is still the damn age of the universe. So even with 1 million cores of processors, supercomputers and whatever you want, and 1 million targets to succeed from, to get a winner, and you just only need one, you still have to spend the whole age of the universe potentially before you find the successful attack. This is insane, guys. This is insane. These numbers are crazy. It almost gives me chills. It's something way bigger than us. That's how cryptography. It's why I'm getting so much into it. It's crazy. So cool. So, all right. So we know this. Now let's make a consideration. The book makes a cool consideration. Let's see. Now that we know, how to quantify security, what influences the cost of each operation, the n-bit security. We gave like a good example with a 128-bit security, right? Now let's talk about Moore's law, because Moore's law, we have to mention it. Moore's law is important in regards to cryptography. You've probably done Moore's law. Moore's law says that every 2 years, what is that? It was the official one. Every 2 years. Well, the gist is that every 2 years the costs of computation are more efficient. We make faster computers every 2 years, right? And so, right, the computer power doubles each 2 years, right? That means, in cryptography terms, and especially what we just learned, doubles every 2 years. That means that we lose, this is good, that means that we lose a 1 bit of security every year. Right? Every 2 years, my bad. Let's keep the same abbreviation, okay? So what does that mean? That that the budget that we now have, the same budget that we have now, if the budget that we have now breaks a 40-bit secure encryption, that means that in 2 years, with the same budget, we can break a 41-bit encryption. Let's make another example, maybe a bit more clear, is that if today, so let's say today, X budget. Well, let's not look at that. Let's make it practical. Today, today's budget can break 40. In, what was the example he made? In 80 years, the same budget can break 80-bit. right? According to Moore's law. And that's why, guys, that's why, and actually I have a little bit of numbers for this to prove this. Why? Because doing 2 to the 128 operations will cost as doing 2 to the 88, okay? Right? So in 80 years, if we had the same situation we had here, 1 million cores, supercomputers, crazy stuff, and 1 million targets, which are gonna increase our odds to succeed in the attack, it means, so add and multiple targets. That means that we can, if we're looking at the same situation, that means that we can go from we can lower to 2 to the 48 nanoseconds. Again, let me show you why I get to 248. Actually, let's see, not assume. So again, so that means that 80 years passed, the same budget that allows us now to attack, the same cost of attacking a 128 in 80 years, thanks to Moore's law, will become the same cost as attacking a 288-bit. So that means that now this 288-bit operation divided by 2 to the 20, which are the number, it's the million cores we're using to break this, divided by 2 to the 20 again, which is the multiple targets. Again, I'm just using the same situation that we had there, the best possible attack scenario, and this will give us 2 to the 48, which, guys, 2 to the 48 nanoseconds is just 3 days. 3 days, not the age of the universe anymore, just 3 days. Why did I talk about this, and what is the implication of what I just went over? Is that what is not possible today in cryptography might be possible in the future, and that's why a lot of cryptographic algorithms were kind of went retired in the recent years, because the computers became more powerful compared to 40 years ago, 20 years ago, okay? Again, according to Moore's law. So what is impossible, what was impossible before is possible now. What is impossible now will likely be possible in the future. And this is how you prove it with numbers, and you calculate it and kind of see for yourself, like how we get to this reasoning. Good. So let me see if I have to. Is there anything else? Also, guys, Moore's law. It's true, that was every 2 years, but we're kind of on a point where it's really hard to get so faster than this and grow at the same pace. I'm not saying it's plateauing, but like kind of. So these are all predictions. Don't put a timer in 80 years and wait to break an encrypt, because it's, it depends. These are, again, predictions, laws, very educated predictions, very educated ways to give hypotheses. What else? What about the 256-bit security? Crazy. That is crazy, crazy, crazy safe. The number 2 to the 256, I don't even know if it's a humanly comprehensible number. And you use this really when you need the maximum long-term security, okay? Now you might think, when is acceptable to use less than 128-bit? Let me make a little Less than 28 bit? Yes. If so when is fine to have less than 128-bit security? When it's justified for a short time. Okay, or for the cost of the implementation. Okay, if you have a little, I don't know, a toy or some little device that is not really important, that it has the craziest encryption, it just needs to have some safety, then obviously it's more cost efficient to implement something to the hardware level, to implement something less than 128 bit. And the example for this, and also when you need it for a short time, this is the example of a smart TV, of a pay TV system. Pay TV systems refresh their keys every 5 to 10 seconds, so even it's fine to use even a 64. What was the example of the book? I don't remember exactly, but yeah, even a 48 or 64 bits. There you go, pay TV systems. You can even use a 48 or 64 bits key because it's refreshed every 5 to 10 seconds and it's cheaper to implement. So again, for business reasons and for time reasons, you can absolutely use less than 128-bit encryption and it will be fine. It will not be a bad thing, okay? So I think it's all for today. And again, remember that 256-bit, it's really freaking impossible to break. Even the author says that even with the scenario of a quantum computer available, it will still be a big struggle to what can I say, to break something like this. Almost impossible. So that's very cool to know. I think that's what Bitcoin wallets use as a private key thing. I don't know. Guys, I just am grateful for you to be following these videos and to, especially if you're hearing these words right now, it means you went all the way through. I hope you understood what I just learned, what I'm studying too, and we're learning together. Cryptography is super cool. I'm seeing some crazy numbers. I'm like, it's really stretching my mind to comprehend this, and it's really cool. So if you appreciate this, give me a thumbs up, let me know in the comments, get in touch with me, I'm here. And yeah, thank you so much for watching. See you next time. Thank you.